Hello, this is IT Taro. This time, I would like to perform a simple simulation of Pachinko. The Python program used in the simulation is also available on the Hobby IT site. I also love Pachinko, but when I find a table that rounds a lot without hit, I think I'm lucky and it's about time I hit it. Also, when I moved the table, the next person immediately took it out. Damn it, I shouldn't have moved. What do you think? I would like to confirm the result by turning it 10 million times to see what the probability is. We will also review distribution graphs for spins and hits, as well as theoretical probabilities and simulations. Even if you don't play Pachinko, I hope you can expand your knowledge of programs and probability. Let's move on to the content. First of all, regarding Pachinko, if a ball enters the center winning slot, there is a chance of about 1/319th a winning lottery. This probability of winning varies depending on the model, but the probability of about 1/319 is the mainstream, so we will simulate with that value. In addition, the probability fluctuates after winning, but the fluctuation varies greatly depending on the model, so this time we will only simulate the first hit. We will check how many times the number of spins will be more hit when spinning 10 million times. Move on. I would like to think about it for a moment. If there is a table that hits 1,500 spins and one that doesn't spin even once, which one would you hit? Without hesitation, I aim for a table that I'm addicted to putting out soon. However, even in cases like this, the zero spin table hits right away, and even the addicting table doesn't hit easily. So, is it right to aim for table that rounds a lot without hit? I wanted to check it out. Let's take a look at a more general, easy to understand example. Move on. This is a game where you toss a coin and guess whether it will come out heads or tails. Suppose you guess which one will come up next when heads have come up 7 times in a row. Are you betting on heads or tails? The probability of getting 8 heads in a row is 1 in 256. Am I the only one who feels like the probability is high? We will use simulations and probability theory to confirm what the probability will be in such a situation. Move on. Let's check the simulation again. The simulation will be performed as shown in this figure. There are 319 balls in the bag, and only one is a red winning ball. Only one piece is taken out each time, and if it hits or misses, it is put back, and from now on, it will be taken out under the same conditions each time. It counts the number of times until a hit comes out, and resets to 0 when a win comes out. Perform this repetition 10 million times and check the rotation speed and hit distribution on the graph. Move on. What do you think the hit distribution graph will look like? As shown on the left, the distribution peaks at a specific number of revolutions. Also, the distribution in which the hit gradually decreases for each rotation number in the middle. Or a distribution that decreases linearly with each rotation speed. It will be one of these. Do you understand, everyone? Now let's do the actual simulation. Here is the simulation program that I used. The programming language will be Python. The reason why there are various parameters is that we have prepared them so that we can tally even every 200 or 2000 rotations. This program is free and easy to run using Google's Colaboratory. Colaboratory is a service that allows you to easily run Python programs on your web browser. It's easy to use, so I'll check it later. This program ran and took 24 minutes to complete. The program is very simple. An integer from 1 to 319 is randomly generated, and if 319 appears, it is a win. It means that the number of rotations when the hit comes out is grasped, it returns to 0 and it tries again. Repeat this 10 million times. Due to the declared array, if it reaches 5,000 rotations, it will be a hit. As a result, it did not reach 5,000 revolutions per minute, so this condition was irrelevant, but it is programmed. Also, the program mainly outputs 3 files. The first is the content that shows the rotation speed and the distribution of hits. Second, the number of rotations is divided into 200 rotations and the hit distribution is confirmed. I prepared it because I wanted to check how much it hits when I spin it about 200 times for 10,000 yen. Third, the number of rotations is divided into 2000 rotations, and the distribution of the number of hits is confirmed. This is to check how the number of first hits will be when the number of rotations in a day is 2000. Since the output data will be separated by commas, it will be read into Excel and graphed. We will check the results that were graphed in Excel. Next, I will check how to use Colaboratory. Search and access Colaboratory in your web browser. Once accessed, create a new notebook. Give your notebook a name. If you paste the above program and run it, after about 30 minutes you will get 3 files as a result of repeating 10 million times. Back to slides. Here are the simulation results. The hit distribution graph looks like this. In other words, the lower the number of rotations, the greater the distribution of hits. How was it? Did it match your guess? I didn't fit. It made me wonder why the first spin hits the most. Also, is it easy to win if you only hit the first 200 spins? The moment I saw it, I simply thought, it is a little easier to understand, and although it is the same content, we will check it with a graph divided every 200 rotations. Move on. Here is the same content divided by 200 rotations. The red letters show the percentage from all hits. The probability of winning in the first 200 spins is 46.6% of the total. In the next 200 rotations, there will be a ratio of 24.9%. I will check the numerical value for every 200 revolutions in detail. Move on. Here are the numbers for every 200 revolutions per minute. In conclusion, the reason why there are many hits in the first 200 spins is because you bet that much, and the probability does not change. Of course, if you hit it, it will return to 0, so the first spin will always bet at any number of spins. The more likely you are to win, the more times you will win. I would like you to see the red dotted frame, but the number of bets is also output in a file. If you divide the number of hits from the number of bets, you can check the probability per one bet. It's obvious, but it's all about 1/319. There are few samples at high rotation speeds, so there are variations, but if you increase the number of samples, everything will be 1/319. In addition, the ratio of hitting up to 400 revolutions per minute is 24.9%. This is because it is a percentage of the total hit, so it will be like this. After excluding the first 200 hits, the percentage from the remainder is still 46.6%. In other words, 46.6% of all 200 spins will win. Next, I wonder if it really matches the theoretical value. I will check the probability of winning at 200 spins. Since there are 200 chances for 1/319, wouldn't it be a probability if we multiply it by 200? I thought and confirmed. Of course, about 62% were wrong, and the results and thinking seemed to be completely different. I'm not sure, so I asked ChatGPT. Move on. After all, ChatGPT was amazing. I got a clear answer. I have even pointed out the points to note. The answer is as follows, but unfortunately, for some reason, there was an error in a simple calculation for the computer. Well, assuming that you can calculate it on your own, in other words, the probability of winning 200 times should be subtracted from 1 by the probability of continuing 200 times without hitting once. I see, wonderful. So I calculated. Perfectly, it became 46.6% and the probability matched. Therefore, it turns out that the probability of winning after spinning 200 times is 46.6%. That means you have about a half chance of winning. Move on. When the number of times that can be turned in a day is 2000, I try to make the distribution of the number of first hits. It looks like this. This was the expected result. 2000 is divided by 319, and about 6 times will be distributed to the peak. The probability of winning once a day or less is about 1.3%, so there are about 1 or 2 out of 100 cars, and if there are 20 cars, there will be cars that will only hit once in 5 days. On the other hand, the probability of winning 12 times or more is 2% or more, so if you have 20 cars, you will win 12 times or more every 2 or 3 days. Move on. Finally, I would like to summarize the results obtained so far. First, is there a rotation speed with a high probability of hitting? But it doesn't exist. The probability of hitting 200 spins is about 46%, and it will hit about half. Next, is it worth aiming for a slamming table or a hitting table? That means it doesn't really matter either. The past state is irrelevant, so even if you are addicted or hit, the probability will be 1/319 every time. The problem with the first coin is irrelevant to the past state, so even if the heads have appeared 7 times in the past, the next probability is 50% for both heads and tails. Next is whether it is better to move the table or to stick and hit, but this is also irrelevant. Theoretically, the probability of winning is only the number of times you try, so there is no such thing as which is better. The next question is how likely it is to be addicted, but in 10 million trials, 4,000 or more always occur. I couldn't confirm that I won't hit up to 5,000 this time, but since it's over 4,000, it's quite possible that I won't hit it all for 2 days. However, the probability of hitting up to 2,200 rotations is 99.9% or more. Finally, there is the question of whether the rotating table is really good. This definitely means that a spinning table is better. The lower the cost per round, the higher your chances of winning. The result is as above. I don't have a deep understanding of random numbers, but if you use intentionally biased random numbers, you may get a slightly different result in a short period of about a day. This time it will be one result using Python random numbers. However, I feel that the result at this time does not deviate greatly from the practical sense in the image, so I think it is like this. In the end, as you all know, it was decided that hitting the rotating table was the best. It also means that it's the only way to win. Move on. If you have any requests about simulations and probability, such as whether this can be done, we are waiting for you in the comments section or site inquiries. Of course, we are waiting for anything related to IT even if it is not a simulation. I can't promise if I can do it, but I will do it if I can. This is the end for this time. We will continue to take on the challenge of making things using IT like this, so please give us a high rating and subscribe to the channel. See you next time.